All right, so we're on page 10, class 12. Today we're going to continue to work with the idea of functions. We have a little bit of 2.1 in here, and then we're going to start 2.2. We'll spend 2 days on section 2.2. And so we're coming back and revisiting this idea that we talked about on, what day is it? What day is today, Wednesday? On Monday, called domain and range, where we talked about the domain being all of the input into the function and the range being all of the output. And domains and ranges are sets of numbers, okay? And so when you represent a domain or a range, you either have to use set builder, not, right? That's cumbersome. So when you represent a domain and a range, you're going to be using interval notation. So let's take a look at this graph here. This is from your book. Here's the graph of some function. We don't know what it is. It looks like it's part of a parabola. Recall the domain of a function is the set of all inputs and the range is a set of all outputs. So if I were asking you to identify the domain here, you're looking for all of the x values. So you start, in this particular case, this function starts here, so you would come down, and that would be your very first x value. Let's call it x1. Your function in this case ends right there, so you would come down. So this interval right here, so notice this looks like a number line interval. So let's call that x2 where it ends. So the interval that would describe that domain would include x1 and it would go up to x2. Okay. The range is all of the output values. So let's make that green. So you look for the smallest y value, which would be right here. And you go up as high as it goes to the highest y value. And everything in between that would represent the range. So let's call that y1 to y2. So the range would be the interval y1 up to y2. And you would include the values here. If we had an open circle here, or here, then we would have an open interval. Okay, but both of these values are included. So this is a visual of the domain and range. I've got a nice animated visual that someone, Ian Winokur brought to the college when he came here. And so here's a function. Notice it's in two pieces. And these little teeny circles here are kind of just a result of the drawing, but they're intended to be solid. So a nice visual to see the domain. So if I asked you for the domain here, you can see your domain is going to be two different intervals that you're going to put together with a union sign. But visually, let's take a look at it. Let's take a look at the domain. Oh, I think that's so cool. Okay, so there's your domain. And if I hid those arrows, you can see our domain goes from, what's this first number here? Oh, that's number 1, so that's 2, okay? So our domain starts at 2, and it goes a little bit beyond 5, okay? Just a little bit, but beyond 6, but we'll say it's 6. So if I were to write the domain for this in interval notation, remember your interval notation always talks about over your x values, always. So you would say it goes from 2 to 6, and then there's a gap. And then you union it. Your union doesn't have a stem on it. It doesn't look like this. A lot of you do that, like, from penmanship, right? Do you even have penmanship anymore in school? And now where would the rest of my domain begin here? Where would I start it? 7, right? And I would go out to 15. Okay. So that's my domain. This entire function is defined between the numbers 2 and 6, including 2 and 6, and it's defined between the numbers 7 and 15. All the other x values, they don't matter because they have no input. Literally, they have no input into the decision here as to what your y value is going to be. So let's try looking at the range now. Hopefully you got a sense of what the animation is going to do. The range is all the outputs. So there we go over to our y-axis. Okay, and what would be the smallest y value for the range here? What would be this, other than someone from this first, second, middle table right here? What would be the smallest y value for my range? Yep, -2, and I'm going to include that. And do I just say -2 up to 6? Because that's the highest I go? No, because of this gap right there. So -2 to, it looks like about, I don't know, 2 1/4. And then I'm going to union this piece. I'm going to put this piece, all these outputs together with my upper piece. So that's where my union comes in. And then I go from 4 to 6. So that's how you would represent the domain and range of a function if you have the graph in front of you. Okay. Any questions on that? All right. So here's a function. This function, we don't have an equation for it, but we do have a graph. This function starts where? Where does this function start? The smallest value for this function, smallest x value. -7 right here. So you're going to include that because -7 is defined. So I put a little bracket there on my, I use my x-axis like a number line. Okay. And how far do I go? Do I stop at 7? Do I stop at 7? I just keep going. How do I know I keep going? Yeah, see, I keep going forever and ever, right across because of this. So my domain are what values of x can I put into this red graph here? And it says, well, your smallest value can be -7, but then there's no limit because this graph continues to go. Okay. So the domain here, I write an interval notation and I include my -7, I put a comma, and then I put infinity with a parenthesis. Okay, you try denoting what the range is at your seats. You try denoting what the range is. So let's take a look. So someone want to volunteer what their range is in interval notation, Tyler? Bracket -2, comma, infinity, right, because notice the smallest output value of our function is -2. And we're going all along here, and it's going to just keep going right off the screen because of this arrow right here. So -2, comma, infinity would be the range. Any questions on that? Okay. So let's continue here. I'd like tables 1 and 2 to do this first one. I'd like tables 3 and 4 to do this one, and I'd like table 5, the back table, because you have the most, to do the last one. And then we'll compare. Okay, put up your flag when you're done. All right, so tables 1 and 2, what did we get for Samantha and Elisa? What did we get for the domain? Yeah. 3, okay, and Alyssa, what do we get for the range? Okay, any questions on that? Okay, tables 3 or 4, anybody want to volunteer the domain for the middle one? Summer? And why did you put a parenthesis on the -4 for folks that may not understand that? Right, this circle is not filled in, which means this function is not defined for -4. They've shown you its coordinates, but it's not defined. And then what's the range? Someone from table 4? Colton? Parenthesis -5? 5 bracket, good. And then table 5 back there, Doug, domain? Yep. And domain, Ethan? Yeah, okay. Oh, bracket, thank you. All right, any questions on domain or range? All right. Okay, let's move along. Sing a song? No, not really. Okay. So now we're going to be looking at evaluate. We did this evaluation of finding values for a function the other day when we had the equation and the table in front of us. And now we're going to look at it when we have the graph. So here's a function. Do you have Chris, do you have your notes? Oh, you did. Okay. So do you want to know where we are so you can follow along? Okay, we're right here. Do you have a pencil? Okay. Okay, so the graph of y equals f of x is given below. And, okay, I'm going to stop this for a minute. No, I won't. Mason, see me after class, please. Find f of 0. Okay, f of 0. So what we need to do is we need to determine when we look at this symbol, because it's new for some of you, they're asking you really to find the y coordinate. That's what they're asking you to find. So in order to find f of 0, that sits right there, whatever that's going to be, you need to find the x coordinate that gives you that value. So you need to know what the x coordinate is. What is our input into this function? What is our input into the function? What is the x value? 0. It's sitting there right there in the parentheses. That's your input. So your input is x equals 0. Your output is f of 0. So let's find f of 0. So we go over to 0 on the x-axis and we draw a vertical line straight up and down until we hit the graph, and we hit the graph right here at 0, 3. So f of 0 is the coordinate, the value 3. So if I put this into my typical xy ordered pair form, this is what the point looks like, but this is the output value when x is 0. Okay? So for what values of x is f of x equal to 0? What do we typically call those points on our graph when your y value or your output value is 0? What do we typically call those points, Tyler? The x-intercepts. So that's what this is asking. Hey, what's the x values of your x-intercepts? That's all it's asking, because it's saying that the output of my function is 0. So now you go along your x-axis, you draw a horizontal line, right? And when you bump in to the graph, that's your first x value that gives you your function value of 0. So f of negative 3 is going to equal 0. And if I continue along, right there I bump into it again, f of 2 is going to equal 0. So when you're asked to find the values for something like this, note you're solving an equation. When does f of x equal 0? So your answer should include x equals 0 and x equals 2. Those are also, every time you write a solution, those are little baby equations. Okay, so x equals 0 and x equals 2 are the two spots on this function where the output of your function is 0. Summer? Yes, thank you. I made a mistake. Negative 3 and 2. Thank you. So at negative 3, the value of your function is 0, and at 2, the value of your function is 0. So remember when we were doing our section 1.1 and we were working with our calculators and we were trying to see where our function hit the x-axis, and we went to our second calc. Notice what we used here. We used, let me clear all this out. Second quit, clear everything. When we went up here to second calc, they didn't say x-intercept. I mentioned it then. I said, remember, we're using this word 0, and this will come up when we deal with functions. Because the x-intercepts now, in most of algebra, you're dealing with functions. Once you get beyond intermediate algebra, you're dealing with functions. So your x-intercepts are what make the value of your function equal to 0. And that's why in your calculator they have that term right there, 0. Because you're trying to find the value of x that makes it 0. So how many x-intercepts could we have if we have a function? How many x-intercepts? How many x-intercepts could we have? If I drew any function up there, how many x-intercepts? Not this particular one, but any function I could draw. Let's see, how about if I drew something like this? And I kept going on like that. Huh? Unlimited, right. There's a line. If I had a straight line, okay, in this particular case, that straight line has one x-intercept and one y-intercept. Right, because remember, we can, for a function, we can have lots of different inputs go into the same output. Okay, so this varies. How many y-intercepts can I have, Tyler? Just one. Because a y-intercept, there's only one x value that's going to give me one unique y value, one output. Okay, if I had 2 points on here, let's suppose I had 2 points on here. This looks a lot like what we did the other day. Notice that would not define a function, because when I draw a vertical line down through there, I would have 2 different y values for the same x values. So you can only have one y-intercept. Okay, increasing and decreasing functions. I actually liked the way your book approached this, because they did it with a story that I think makes sense. And I think the idea of increasing, decreasing, and constant functions makes a lot of sense. And I think if you put a little story to this, so for those of you who are actually reading the book, these would be the pages you could find it, 229 and 230. Okay, so this is a little story about a person that has a fever due to the flu. And what is, at the time we're recording this fever, the initial what is the initial temperature of this person's fever? What is the initial temperature? Mason? 101. So if I asked you what is the initial temperature, then what you're looking for, this word initial means time is equal to 0. So you go to 0. Now notice, what would this x-axis be? Well, it's actually x equals 0 here, because it's x and y instead of t and f of t. So you go to 0 and you come up here and you see f of 0 is defined to be 101. So the initial temperature is 101 degrees Fahrenheit. All right. So over what open interval? Now this is important, because this is really sort of an arbitrary thing about using intervals to define when a function's open, decreasing or increasing or constant. Some books use open intervals. Some books use closed intervals. Our particular text always uses open intervals. So notice I have here, over what open interval. So that's something you want to make a little note of in your notes. You want to either circle that or put a little asterisk and make a note that anytime you're talking about intervals where your function's increasing, decreasing, or constant, it's always going to be represented by an open interval. And what does that mean, an open interval? What does it mean to be an open interval? How do you know that an interval is open? No idea. Think about interval notation. Think about interval notation. Do you know how to make an interval, Kenneth? It's blowing your mind? Okay, let's go back to domain for a minute. So here we represented the domain and range with interval notation. This is not an open interval and it's not a closed interval, okay? What would I have to do to make an interval open? 2 parentheses. What would I have to do to make it close? 2 brackets, right. So when we're talking about increasing, decreasing, and constant functions, and the intervals over which these functions are increasing, decreasing, or constant, we're always going to be using interval notation with parentheses. Okay? So if we looked at this first picture, this first scenario, the little story in your book goes that, the person woke up and they had a temperature, but as the day went on, their temperature started to decrease. And so they started to draw a graph. recording their temperature. Okay, very mathematical person. I wouldn't be doing that. I'd probably be playing a video game. No, I'm not millennial, but probably doing a crossword. Okay. So how long, so what is the domain for this first picture? How many hours is this function, in the very first picture, is this function defined over? 3. It goes from 0 hours after 8 a.m. to 3 hours after 8 a.m. So the time would be from 8 a.m. to 11 a.m. Okay? And notice the temperature, which is your output, the actual temperature, is starting to decrease. So over what open interval is your temperature decreasing? Remember, it's always defined based on your independent variable, what's sitting along your x-axis. So the open interval here would start at 0, which represents 8 a.m., and it would end at 3, which represents 11 a.m. So it's not the coordinates of a point, it's an interval over x. So the temperature f of x falls as x increases over this interval. So as x gets bigger and bigger, my curve is getting, my temperatures are decreasing. So we say that the value of this function is decreasing over this interval. Okay, so now we're going to move on. Well, I did too much work making this graph. My temperature starts to increase. Okay, so over what open interval is your temperature increasing? Paul, could you help me with that? 3, because we're going to start right here. And we notice we go to 5, because for any value of x along this point, if I take x at 3.5, and then I take x at 4, my temperature at 4 hours after 8 is less than my temperature at 3.5 hours less than 8. So that's a more formal definition. So we say 3, 5. I think it's intuitive. Yeah, Chris? As I mentioned a few minutes ago, that it's arbitrary whether you put the bracket. If I put the bracket, say right here at 3, then yeah, it's not clear whether, you know, at 3, what are you doing? You know, that's sort of the point where you're neither decreasing anymore or increasing anymore. So some books, Chris, put brackets around these, and some books just put open circles. It's sort of like your beginning and your end point, but you're not including them. You do, and we're saying that these are all open intervals. That's why we're using parentheses, okay? So what open interval is your temperature remaining constant? So what would be the open interval where my temperature was remaining the same? Here we go, Ken, good. What, parentheses what? Good, all right, okay. All right, now the other idea that we have here goes along with this question. At what time is your temperature at its lowest? So if you go back here and you look at all 3 of these, what time is your temperature the lowest? Let me see if I can erase all this mess that I have here now. Let's take all this out. So if you look at these graphs, what time is your temperature the lowest? Time, 11 a.m., which is 3 hours after 8. If you read your scale, it's at 11 a.m. Okay, a.m. Okay, so that point right here is another idea that we're going to discuss. It's called the relative minimum. Okay, I don't know if that's the lowest my temperature is going to ever get, but right now on this particular graph, this is the relative minimum. Okay, it's the smallest y value that you see between 0 and 7. So if this defined the whole scenario, this last picture, you could actually say that at 11 o'clock with a temperature of 98.6, it looks normal. That was your absolute minimum. But in this class, we're just going to talk about relative. If you look in this neighborhood right here, in this neighborhood, if you just kind of zoom in right there, that is your lowest temperature. So it's called relative minimum. Okay, so let's take a look. Your book gives you this more precise definition of when something is increasing and decreasing. And it's rather abstract, but the idea, if you apply what we just did, I think you'll understand the abstraction here. It says f. F is the name we call our function. So whatever your function's name is, you just write it, just the letter. You never write f of x. You just say f or g or p, whatever you're calling your function. So f is increasing on I. Does anybody know what I stands for? Interval, right. F is increasing on the interval if f of x1 is less than f of x2. So they've given you 2 points right here. They've given you the point 1, 2.17, and they've given you the point 6, 23. So x1 would be the value 1, and x2 would be the value 6. So 1 is less than 6. And so if its corresponding output value is less than this corresponding output value, my function must be increasing to get from this point to that point. And that's what all of this symbolism means here. F of x1 is 2.17, and that's less than 23. That's how you read that symbolism. To reverse it, notice here, x1 is less than x2, but its output value is higher than the output value for x2. So my graph in between on that interval must be decreasing. And similarly here, x1 is less than x2, but notice all of my output values on that interval do not change at all. And that's the formal definition of when a function is constant. So again, this is all from your book, and it's more formal than we really need to be. But that's how they define in mathematics when something is increasing and decreasing or constant. All right, so now we hit this relative maxima and relative minima idea, and we just played a little bit with it. So again, all of this is being described to you generically in terms of function notation. Okay, so let's make sure we understand what each sentence means. When a function changes from increasing to decreasing, so let's take a look at this very first picture. This function on the interval of negative infinity to c is increasing. If you just follow my line, it's increasing right up until, boom, we get to that highest point. What's the coordinates of this point right here? What would be the coordinates of that point? If I put my little parentheses. What's the value of x and what's the value of y? C is the value of x, here it is. And my output will always be f of c or g of c, whatever your function's name is. It's always f of whatever your input is. My input's called c, so my output's called f of c. Okay? So this point right here defines a relative maximum. Okay? It defines a relative maximum because after this point, your function starts to decrease forever and ever. Okay? So, well, at least it looks like it's starting to decrease. We really don't know. This function could kind of continue on and do this kind of thing. We don't really know what it's going to do. It looks like it's just going down. Okay. What'd you say? Yeah, it just continues. That's your domain. So in other words, you know that the domain for this, okay, what is your domain for this actually in your range? What's the domain here? Okay, so we know this is going to keep going, right? Keep going, right? And we know that this is just going to keep going and keep going. So could I have a value here and have my function defined? Could I have a value here, 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 and here? So what's my domain? Negative infinity to positive infinity. It's all real numbers. What's my range? The way it looks right now with this just continuing to go down. Yeah, negative infinity, not to c, but to what? F of c, right, because that's my output value, right? Okay. So this is a relative maxima. And then if we have a function that's decreasing, and it hits some point, and then after that it's turning around like you're negative, negative, negative about math, and then you hit a point where, oh, I'm positive, positive, positive. That point, the same point, C, F of C, is called a relative minimum. Okay, now here's the most important idea about all of this, is that when your book or any story asks you for a relative minimum or a relative maximum, they don't want you to give the coordinates of that point. They want you to say, what is that smallest output, or what is that largest output? They're only interested in the output value. So when they're asking you to define what a relative maximum is, you're looking for the value. So make sure you underline this in your notes. You're looking at the value of the relative maximum, which is your output value, F of C. And if they're asking you for a relative minimum, it's the value, F of C. Okay? So a lot of times students make the mistake of reporting both coordinates. If you were looking at a cost function and you wanted to know your highest cost or your lowest cost, you're just going to report the cost, the value of the cost. Okay, that's just your output. Okay, or if you're looking at changes, global temperatures, and you know what's happening to the ice in the Arctic or the Antarctic, you're going to be looking at the temperature, the highest temperature of the ice, or the lowest temperature of the ice, or the highest degrees. You're only interested in the output of your function. Yep, Chris? That's right, just the F of C value. Right, so let's take a look at an example here. So down here, when it says H, when it says any relative maxima and the numbers at which they occur. So look at how this is phrased, and this is exactly what your book does. The relative maxima, and the reason they have an A now is because you can have more than one. So A is plural, A makes this plural. You can have one or more maxima, relative maxima. It's not absolute. You could have a function like this, Mason. Let's take a look real quick. Let's say we have polynomial function like this. Okay, you have in this neighborhood, that's your king of the mountain. That's your first relative maxima. And when you're in this neighborhood, that's your second relative maxima. So depending on your function, you can have multiple relative maximums. That's why they call it maxima. In this particular case, you only have one relative minima. All right, but they use the A because it can be plural. You can have more than one. So notice here what I'm trying to point out is that when you see relative maxima, you're just giving the output value, and it occurs at, and what's going to go here? It occurs at what would be in this spot. This is your output. What's this going to be? Your input. So your maxima and your minima are the output values, and then you can say where they occur, what the X value is or the C value, whatever you're using to label your axes. So this is sort of like your little group work today is this next problem, number 8. You could take 15 to 20 minutes. I'll put on some music, use your flags if you have any questions, and work with your groups on this particular idea. Okay, so this function, because of these two arrows right here, the minute you see two arrows on either end of a function, you have a very easy answer for the domain. What is that answer? Anybody? Negative infinity to infinity. You could say all real numbers. Yep, whatever you want. Either of those two are totally acceptable. All right. So the domain here is all real numbers. This function has no limits on it. Okay, what's the range here? What's the smallest value of the range? Right, there isn't one because it's negative infinity, so we include parentheses here because I shouldn't say the word include. We use parentheses there, negative infinity. And is there an actual maximum value here for the range? It goes as high as 4. Okay. Oops, and we include 4. Okay. Keep your eye on me. Keep your eye on me. Now remember, don't confuse what we just did, which is where over what intervals is your function increasing, decreasing, and constant? Everything is open. This point 4 is defined on your graph. It's right there. So you have to put brackets, little staple there. Chris, did you have a question? Yeah, assume that it keeps going down. Yeah. Okay. The zeros of the function f. Remember, they're just asking now for what, if any, are the x values that make your function 0. And that's the x values of your x-intercepts. So your answers here should always be in the format of x equals. So what are those values in this particular case? -4 and x equals 4. You could also have x equals plus or minus 4 if you want. So I'm not interested in the coordinates here. I'm just interested in the values of x that make your function equal to 0. Okay. Now f of 0 says if you go to x equals 0 and draw a straight line through x equals 0, which is your y-axis, where do you bump into the graph? What is the y-intercept? That's just another way to say what's the value of your y-intercept? Y-intercept value. That's all that's saying. What's the value of your y-intercept? And it's just the output value. So you go right here and you say, oh, my y-intercept is, the coordinates are 0, 1. My value at x equals 0 of my function is f of 0, which is 1. Okay, the intervals on which f is increasing. Okay, so I look for my high points because I know there are my 2 high points. Everything before my high point is the interval that I'm increasing. So in this particular case, I'm going from -infinity to -2. And since I have 2 high points, I'm going to union that with another set. And I'm increasing here. The interval before I get to that high point is from 0 to 3. And these are all open intervals. Okay. Now, decreasing is just the opposite. You go on the other side of the high point. Here's where I'm decreasing, and here's where I'm decreasing. So my intervals from which so this point plays a pivotal role. Notice that -2 is the end point for this increasing interval, and it's the beginning point of this decreasing interval. The beginning point of this increasing interval is the end point of that decreasing interval. So it goes from -2 to 0, and then we go from 3 to -infinity. Okay. Now, Caitlin brought up a really good question that I just wanted to mention. Yes, thank you. Positive infinity. Because it's always over the x values. Thank you, Chris. So if you had a graph that looked like this, well, let me make it even simpler. And this is one of those subtle points about increasing and decreasing. If we go back to our definition, notice when you're increasing, you have to have an x1 value and an x2 value. And you have to always, your y values always have to be increasing on that interval. When you're decreasing, you have to have an x1 value and an x2 value, okay? You have to have something on either side of that. So if you, let's go back here. So I'm wondering if my original graph here had something like that. Yes, it does. So I'll come back there in a minute. I'll show you Caitlin's question in a minute. All right, so let's put that back where it belongs. Okay, values of x. So now they're just asking you for the values of x. It could be using an interval for which f of x is less than or equal to 0. So what is f of x? That's the picture of your graph, and if it's less than or equal to 0, thank you, greater than or equal to 0, if it says greater than or equal to 0, you're just basically taking your x-axis and cutting away anything below the x-axis, because this is just saying, when is your function equal to 0 or positive? That's all it's saying. What are the x values? So you can just basically blank out everything. Ooh, that's not the symbol I wanted. I'm trying to get fancy and I don't have time to get fancy. So you're basically just saying, okay, I'm going to take this whole area except for where it's 0, and I'm going to take everything below that and just cut it out. So my function is 0 at -4 and 4, and everything in between there, I'm positive. So this particular question would be answered with the closed interval -4 to 4. Everything between -4 and 4 in this picture, everything is above the x-axis or right on the x-axis. Okay, now here's any relative maxima and the numbers at which they occur. This is exactly out of your book. This is how you'll be asked questions on your homework. So relative maxima here, you have 2 of them. You have one in this neighborhood right here, who's the top pin, and one in this neighborhood, who's the top pin. Okay, so this relative maxima is, what's the y value here? It's 4, and the y value here is 2. So your relative maxima is 4 and 2, and it occurs at, where do they occur? Well, let's find the x values, 2 and 3. Occurs at x equals 2 and x equals 3. What is it? Yeah, -2, okay. -1 for Linda. All right. Then relative minima. What's the relative minima? You go right here to this low point. It occurs at 0, but the relative minima, the lowest point right around in this neighborhood, the lowest point is the number 1. So the relative minima is 1, and it occurs at x equals 0. Okay. The value of x, is this different on your paper? Because do you have this? Equals 3 on your paper? Okay. Okay, the value of x for which f of x equals 3. Okay, so you go and you put a vertical line right through y equals 3. So here we go, y equals 3. I'm going to go right through y equals 3. And I touch my graph in 2 spots. I touch it right here at x equals -3, and I touch it right here at x equals -1. So x equals -3 and x equals -1. Again, remember, when you're doing that, it's like solving an equation. You want to put in x equals. And then what's your last one here say? F of net 5. I don't know why mine is different than yours. Okay. Is f of 5 positive or negative? So you go to the input value of 5. You come straight down until you hit your graph. And is that below or above the x-axis? It's below. So your value of f of 5 is negative. Any questions on that? Okay, so let me go back. I'm just going to move this picture for you for a minute. And I'm going to erase all this. You'll still have all, oops, I hope I was recording. Yes, good. Okay, so here's another whole new picture for you right here. Let's just do this together a little bit. What's the domain here? What's the domain for this? Chris? Okay, and bracket on -7, infinity, parentheses. Okay, what about the range? Smallest point, smallest value here is -2, and I include it, so I put the bracket. Do I have any maximum value in my range? Because this is going forever and ever and ever. So infinity, parenthesis. Oh, my comma. Okay. All right. So the point that I want to make here, I think we could finish the rest of this, is what's happening right there. Okay. So this is subtle, but it's important. If I asked you for the relative maxima of this function. You might be tempted to say 5 and 6. But you have to have, remember, your definition is your function, the definition for a relative maximum is that it's the point right here, and to the left of that point, your function is increasing, and to the right of that point, your function is decreasing. So when you have this point right there, do you have an interval before negative 7, 6 where your function is increasing? No, there's nothing here. Nada. There's nothing over here. Okay? So you can't say that 6 is a relative maximum because there's nothing to the left of it. You always have to be on a hill or in a valley to define maximum, relative maxima, and relative minima. So thank you, Caitlin, for answering that, asking that. Okay. So even and odd functions. This is a situation where students intuitively understand what an even function is and an odd from the picture, but they often will have a hard time showing it algebraically because they don't understand the notation here. So first of all, let's talk about what does it mean to be an even function. What it means to be an even function visually is I could take this graph and fold it over the y-axis. And for each value to the right of the x-axis, I would be at the same, so let's say I'm at 1 or 1.5 or 2, wherever I am on the graph on the right-hand side, when I fold it over, it's going to have a partner on the other side at exactly the same height, but the x values will be opposite. Okay, the x values will be opposite. So this is how we note it symbolically. If my x values are opposite, that's what these two things inside say. If my inputs are opposite, notice what my outputs are. They're exactly the same. So I've started a table here for you. And what I'd like you to do is try to follow along with this picture. Where are we starting in the table? 2.5 and negative 2.5. Okay, so let's make this large. Let's blow this up. Let's show the symmetry. And I'm going to move my x coordinate along until I get to, let's show the coordinates, till I get to 2.5. Okay, oops, can I get exactly to 2.5? Maybe not. I don't think. There we are. So on your table at your seats, what are you going to fill in for the coordinates at 2.5 and negative 2.5? Exactly the same output. So when my x values are opposite, my outputs are the same. That picture is exactly what that notation says. So you have to be able to go from specific values to the abstraction here. This says if your x values are opposite, your y values are exactly the same. And that's what's going to happen when you fold that over. Okay, it's a mirror image on either side of the y-axis is another. So I want you to, I'm going to stop at some points and I want you to fill in your table. So I'm going to move this along. Okay, there we go. So fill that point in your table. Can't see it? I've made it as large as I could, unfortunately. Huh? Okay, and then output values, are they the same? Are they the same? What are they? 4.13. Okay, so this is how I would write it to show that this is an even function. F of 3.08. What does this represent? F of 3.08. What's another way of representing that notation? F of 3.08. What is F? And what is F of 3.08? And what is y here? What is f of 3.08? 4.13. So f of 3.08 is 4.13. The question to show whether something is even or odd is to say, if I look at its opposite value, if I plug in negative 3.08, is the value of my function exactly the same? So let's go over here. Negative 3.08, what's the value of my function? What is f of negative 3.08? It's 4.13. Cool. All right. Now, I don't have the equation, so I do have the equation. So you could do this forever and ever for every single value of x, and you still could not say it's even. All right, because it's impossible to put in specific points. So to show whether a function is even or not, you have to show this for all x. So this is what you do. Here's your function right there, x to the fourth minus 10x squared plus 9. So you put in negative x for x. So where you see x, you replace it with negative x, and you have to use parentheses. 10 times negative x squared plus 9. That's my input. And you're trying to show that that equals the function when you input x. Well, that's just this right here. X to the fourth minus 10x squared plus 9. So does the left side equal the right side? That's the question. Well, oops, I didn't mean to do that. Negative x to the fourth is what? X to the fourth, because this has a negative 1 right there. Negative 1 to any even power is 1. X squared plus 9 equals x to the fourth minus 10x squared plus 9. Okay. So you have now shown that f of the opposite of x equals f of x for all x. That's how you show something's even. For odd, it's a little bit different. Okay. Okay, if you came in 20 minutes late, you can give me 1 more minute, please. All right, for odd functions, it's a little different story. For odd function, look what happens when you put in opposite values. You don't come straight across. Odd functions are symmetric about the opposite, around the origin. So you come here and then you go down here. So to show that two functions are odd, when you put in the opposite values for x, the y values are opposite. Okay, so that's odd function. Sorry, I had to rush that a little bit. Okay, have a good day. See you Friday. If you did not pick up your quizzes,